Hello, everyone. My name is Karthik Mandakolathur. I'm a product manager at NVIDIA. Before I start my presentation, I would like to set the context. Last week, thanks to NVIDIA, we had a couple of free days. So I had the chance to take my family for a whitewater rafting. And the trip was great fun. And as I was reminiscing about that trip on the way to Denver today, I realized that all that fun was possible because the safety aspect of the trip was guaranteed. We had a very experienced guide who was by our side. In the same line, confidential computing provides that foundational infrastructure layer, which is safe and secure, into which developers can onboard their sensitive AI applications. Traditionally, for protecting data in transit, you use technologies such as VPN, TLS. With TLS, you can encrypt the data, the sender encrypts the data, the encrypted bytes travel to the network. Even if somebody snoops in the network, they will not be able to infer what the data is because they don't have the key. And eventually, when the data hits the receiver is able to decrypt it with the appropriate key. For data in store, similarly, we may use something like AES 256 for encrypting the data. Even if somebody walks out with the storage drive, they cannot do much with it. There has been a gap, though, just data in use. Data in use has been mostly unprotected, but of late, CPU vendors, especially Intel with Intel TDX, AMD with SEV SNP, they have solutions to protect the data in use. And this is directly related to AI use cases. So there are a couple of use cases shown on the far left in the slide, but there are a lot more. The first one is model as a service, where some organization invests tens of millions of dollars to develop a model, and they may have to deploy the model in remote places. It may be stores, retail stores in geographically diverse locations where they don't have much control, or it may even be an oil rig of some sort. How can they guarantee that their IP is safe in those remote locations? So confidential computing provides a framework and a layer and some kind of guarantee so that their IP is not infringed. It's not just the inference use cases, even for training or fine-tuning use cases. Organizations' proprietary data is being used. So during that phase, during the training phase, you don't want that data to be stolen. The second use case is in the bottom right, which is the federated learning use case. Here, multiple organizations come together, and they want to build a kind of a super model, which represents the learning of all the data they have. Although they are not able to explicitly exchange data with their partners, they are interested in building a model that assimilates the learning from all the data sets they have. And again, confidential computing is a great way to accomplish this task. This could be a bunch of hospitals trying to build a model to identify diseases, or it could be a financial institution trying to do some kind of modeling for fraud detection, where they cannot explicitly share the data itself due to compliance reasons. So to address this, NVIDIA introduced confidential computing first time with the Hopper GPUs. We are able to provide complete VM isolation, and we also, alongside the hardware support for the security, we are also able to provide, we have cloud services for the attestation part. And for the users can leverage all of this without making any change to their code itself. So that's mostly a lift and shift they have to do to use the confidential computing environment. With Hopper, we introduced a single GPU pass-through. That was the first confidential computing mode we introduced to the market. In this case, and this is based on a virtual machine. At the end of the day, the developer gets a confidential virtual machine they can use to deploy their application in. And in this case, the CVM has exactly one GPU pass-through. So it's one CVM having one GPU. And all the communication that happens between the CVM and the GPU is encrypted. And there are firewalls established in the GPU side to to prevent access from the hypervisor and the host OS. To contrast that with when CC is off, you can have a situation where there is a malicious actor in the host OS or in the hypervisor. They have complete access to the memory pages in the CVM. They again have unrestricted access to critical regions of the GPU, for example, the video memory. So with confidential computing, especially the single GPU pass-through solution, we are able to establish a trusted execution environment, which comprises of a CVM and one GPU pass-through to it. Attacker cannot really snoop the CVM itself because of the confidential computing capability of the CPU, be it Intel TDX or AMD CVSNP. They cannot access the GPU either because firewalls are established. The GPU also has a hardware root of trust to enable this capability. The hardware root of trust is essential to make measurements in the GPU itself. This can be what fuses are burnt in the GPU, what configuration is running in the GPU, as well as and it's also signed. So there are signatures burnt into the GPU, because of which eventually when you get these measurements out of the GPU, which is what we call as an evidence, it's a signed evidence which can be used for attestation purpose. I mentioned that the external entities cannot access the pages inside a CVM. Even the GPU, which is hanging off the PCS which represents the system, is an external entity, and it won't have direct access to the virtual pages, the pages in the virtual memory. And for this reason, we introduced a concept of bounce buffer in the Hopper confidential computing solution, where we have regions of memory which are there both in the CPU side in the system memory as well as in the shared memory side in the GPU, which are outside the protected region, which can be accessed from the other side. So for example, if a CVM, if an application which runs inside the CVM wants to write to the GPU memory, under the hood, what happens is the data that is sent by the application is encrypted, written to the unprotected region of the system memory, and it's signed as well. And the GPU copy engines copy it over to the unprotected region in the GPU side, and then eventually it's decrypted and copied over to the protected region in the GPU memory. So every transaction from the CPU side to the GPU side, also in the other direction, it hops through these bounce buffers. That's hence the name bounce buffer. So this is required to enable data movement. Of course, in a heterogeneous workload like AI, there's a lot of data movement between CPU and GPU. To facilitate that, we have this concept of bounce buffer. However, even if an external entity tries to access that region, they won't be able to interpret the data because it's encrypted. They don't have the keys to decrypt it. So far, the solution I've talked about with Hopper, it's a single GPU, single CVM solution. Of course, our customer wanted to run larger models. And for that, we introduced a mode called protected PCIe with the Hopper. And in the case of protected PCIe, it's supported in systems with 8 GPUs and 4 NV switches. Now the trusted execution domain not only comprises of the CVM, the 8 GPUs, it also includes the NV switches, because that's also an attack surface. So just like we attest the GPUs, we attest the NV switches also, which are part of the TEE. And the data between the CPU and the GPUs are encrypted, much like same way as we did, as it was done with the single GPU pass-through. And all the GPUs now have they can exchange data amongst them. So communication protocols such as Nickel can be used with full performance. So in terms of the coverage, software attacks to the from the host and the hypervisor, that cannot happen because in the CPU side of things, we have Intel TDX or AMD SEV-based CVMs, which will prevent access to the pages in the CVM. In the GPU side, firewalls are established, so there cannot be any direct access for critical regions from the host or the host OS or the hypervisor. Physical attacks to the PCI Express bus itself is mitigated because that traffic is encrypted. So physical attacks on the NVLink is out of scope. So that's part of the reason is the traffic between the GPUs in the solution is clear. That the NVLink traffic is not encrypted, but then it's a proprietary protocol, so we don't expect anybody to be able to interpret the data that flows through it. So with this solution, the advantage is now we have 8 GPUs in the trusted education environment, and there's not much of a performance penalty. In fact, we observed 100% same performance as without enabling confidential computing with protected PCI for a Llama 3 model. So I went over a couple of modes which are supported in Hopper, namely the single GPU pass-through as well as the protected PCIe. Now I would like to go into a bit more detail in terms of how the initialization sequence itself works to set up the system. NVIDIA provides open source tooling to set up the confidential computing mode. So you can pick between, say, protected PCIe or single GPU pass-through mode, and you can use that tool to set the mode. For the mode to take effect, you need to reset the GPU. So that's the first step, and that's when it takes effect. And the first thing that happens inside the GPU when it knows that it's coming up in a confidential computing mode, the firmware goes in and scrubs the GPU state and the memory. So that way, there is no leftover state from the previous tenant, and it's sanitized for the user to use. And in addition to that, it also establishes the firewalls. And the firewalls in the GPU will prevent access coming in from host OS and the hypervisor to crucial regions in the GPU, for example, the video memory. And after establishing the firewalls, it lights up the PCI Express bus, and it's discovered by the CPU. And then the driver loads up. When the driver loads up, it establishes a SPDM session with the GPU. It collects the GPU measurements, which will help identify if the device itself is legit, if it is having the right configuration, if it has the right firm vBIOS burnt in. And it also collects the measurements from the driver and the host side. Now, all of those measurements, which are signed, which acts as evidence in the attestation transaction, that is passed to the attestation service, which is either run locally or remotely. And at the end of the day, the fundamental goal for the attestation process is to, one, make sure that the infrastructure that's being used is truly what the user thinks it is. If it is a H100, if it is a single GPU pass-through mode, or if it is a protected PCI mode where 8 of the GPUs are being passed through. So you make checks for whether the system is legit, whether it has the right version of, whether it has the right configuration, which is the right security posture. And depending upon the attestation result, the user can make a decision whether to run their workload or not. And that's when the CUDA program can be run. And subsequently, after they're done with the use of the GPU, they can issue a PFFLR to reset the GPU. And then that takes the state of the firmware back to step 3, which is sanitizing the GPU state and the memory so that the subsequent users don't have any leftovers come out from this user. So far, I talked about what Hopper provides, what are the capabilities of Hopper for confidential computing. With Blackwell, our primary focus is to improve performance. And the way we do it is we reduce the overhead for the CPU-GPU communications. I'll go over the details in the next slide. We are also able to scale better with Blackwell because of inline encryption, and we are able to support multi-node confidential computing solutions at a much larger scale. And security-wise, Blackwell hardware is capable of TEIO, which means it's a hardware capability which can be used to extend the TEE from the CVM to include the GPU also. So there are three main pieces of technology which come together to eliminate the bounce buffer. The first one is IDE, which is inline encryption and decryption through the PCI Express bus. And the second feature is the TE-IO capability. With TE-IO capability, the GPU can become part of the TE environment in the CVM natively, so there's no need for any bounce buffer. Data from the CPU can be encrypted and sent directly to the GPU, and then the GPU can decrypt and use it. So we don't have the staging of the data transactions as we did when there is a bounce buffer. However, for these two, the IDE and the TE-IO capability to come to fruition, we need to have a control protocol, TDISP, enabled in the system. And TDISP today is not at upstream. So until we get TDISP from the software side, we really cannot, we still have to continue using the bounce buffer, even with Blackwell. So for multi-GPU solution with Blackwell, we have a multi-GPU pass-through mode. In this mode, again, it's meant for 8 GPU, 4 NV switch systems, and 8 GPUs for 4 NV switches can be passed through to a single CVM, or we also support smaller granularities like 2, 4, 6. So within the same node, you can carve it out between multiple CVMs. The CPU-GPU transfers are encrypted. Again, the encryption can either happen, today it can happen through bounce buffers. In the future, we'll have, once TDISP is enabled, we can eliminate the bounce buffers so we can get better performance. And the GPU to GPU traffic is encrypted. So this is an improvement compared to Hopper, and that's the reason why we could carve out different CVMs within the same node. If you recollect, the Hopper protected PCIe, it's all 8 GPUs in the system are passed through the CVM. It's either all or none. So the only configuration with protected PCIe Hopper we support is 8 GPUs being passed through. In terms of performance improvement, we have observed that the newer CPUs, they perform better with bounce buffers, up to 3x performance improvement with AVX 512 capable CPUs. And once TDISP is available, we can even see line rate PCI Express data transfers between CPU and GPU. And NVLink transfers have doubled. That is a native improvement in the NVLink fabric, which comes with Blackwell. So here is a quick summary of how NVIDIA enabled confidential computing through its various releases and its platforms. Back in our 550 12.4 release, we enabled single GPU pass-through for Hopper. Subsequently, we added multiple GPU pass-through for Hopper, along with, that is protected PCIe in 12.8, our 570 driver. And more recently, we introduced support for single GPU pass-through with Blackwell. So that's where we are. In the future, we'll add more capabilities, especially in the Blackwell line, with the future releases. And as we get more upstream content, like for example, TDISP, we can anticipate better scale and better performance with our platforms. Again, in terms of the foundational requirement, we still require, since it's CVM-based, we require from the CPU side, whether it's Intel or AMD SCV-SNP or Intel TDF-capable CPUs. And the GPU side, as I said, Hopper, we have a track record of, we have at least multiple releases. We have multiple modes in Hopper for confidential computing. We started introducing confidential computing for Blackwell as well. So I just wanted to touch on attestation service. I just mentioned attestation a few times, but just wanted to dive a bit deeper in terms of the services we currently have to support attestation of the infrastructure. So at the end of the day, what the user wants to do is they want to confirm that they are running their workload in a legit system and in really a hardware they think they are running in. For that, they will have to take measurements from the infrastructure and then compare those measurements, what's technically called evidence, against the golden measurements that are stored in the RIM service. So we call it reference integrity manifest. These are stored in the RIM service. So they have to compare. So the comparison of the measured value with the golden value, that can be done using attestation service, or in a different model. I'll go over it in a moment of time. It can be done locally also. The other aspect of attestation is to check if the certificate is still valid. So at a point in time, a RIM may be valid, but later we may discover that there is a CVE or some other security, or for some reason we want to revoke that certificate. So that revocation step is done using a service called CSP. So in terms of the entire flow, this is how this represents the multiple flows which are possible for attestation. Probably the most direct one is the direct to NVIDIA solution. In the direct to NVIDIA solution, we provide a Python library which the developer can install inside the CVM. And using that, they can point to the NVIDIA attestation service, remote attestation service. And the measurements which are taken from the infrastructure is passed to the service. And the service, in turn, first checks if the signature in the request is legit. It's actually true. It matches. Once it matches the signature, it uses the RIM service to validate and compare whether the measurements match with the supported system. And then it also checks if that cert has been revoked or not. So after that, it provides the token back. Based on the token, the user can make a decision whether they can run their workload or not. The local verifier or a hybrid attestation is a slight variation where the check whether the measurement and the evidence match doesn't really happen in the remote service. It can be done locally. So the advantage of doing this is they have more control in terms of how they perform the checks and how frequently they do it. But the disadvantage is it may not be up to date. So when you go direct to the NVIDIA service, it's going to be checked against the most recent information. Whereas if they check locally, then it may not have the same kind of fresh data which for used for checking. There is also a broker workflow where in case we're using an infrastructure which uses more than the GPU, let us say you want to also attest the Intel CPU, for instance, you can have a man-in-the-middle service which kind of aggregates the requests, attestation requests, not just for the NVIDIA GPU, but also for other vendors, and then provides a composite response back to the developer. Now, if the environment itself is air-gapped, or for some reason they don't want to query the cloud service, the cloud attestation service frequently, there is an option to run the whole service locally. NVIDIA provides a Helm chart for this. You can install the Helm chart in your local infrastructure, either accessible either in the node itself or accessible in the intranet. And this service essentially acts as a cache. It periodically goes to the NVRAS service, gets the latest RIM information at the point in time, and then the local service is what is used for attestation by the program run by the user. Some CSPs have existing attestation workflows, and they may want to integrate the NVIDIA attestation workflow into their workflow. And for this, they may need more control. They may sign their own claims. So they essentially front-end the entire attestation request response. We support that as well. And this is an increasingly, in this case, the CSP has a lot more control instead of using a prepackaged set of services. That's pretty much what I had. This is my last slide. And the key thing I wanted to highlight is NVIDIA introduced configurable computing with Hopper, and we have multiple modes in Hopper to enable single GPU and multi-GPU workloads. We continue to add confidential computing support with Blackwell, and we will do so with the newer platforms. And as and when we get upstream contributions, we'll also improve performance and enable the newer capabilities in the Blackwell GPU. And it is not just the GPU firmware driver, it's a full stack solution. We are also investing in cloud services for attestation. And the whole idea is to build a solution which the developer can just use to lift and shift their workloads into a more secure environment. Thank you.
Do we have any questions?
Yeah, please.
Yeah, please.
So I have a couple. I couldn't figure out where is the buffer space in your pictures.
Sure.
Can you just explain that? That was one.
So I think the question is, where is the bounds buffer allocated?
Yes. Where is it in this picture?
Sure.
I don't understand.
Yeah, it is not clearly shown in the picture. So the bounds buffer, so CVM, the pages inside the CVM cannot be accessed by external entity.
Yes.
But then there is system memory, CPU system memory, which resides outside the context of the CVM. There is still memory available outside the CVM. So we reserve a memory region there. We allocate that memory region. Bounds buffer is just outside the CVM. But then it's not required. And then that's one region. Similarly, there is also bounds buffer allocated in the GPU side.
So in this diagram,
So
I guess it would be...
It should be like, we should have a box here and a box here.
So I
Can't see where you're...
maybe. Yeah.
So we should have a box there.
Inside or outside?
It is not part of the, you're right, it cannot be part of the TEE, it's outside.
It's outside the yellow box, right?
Yes,
it's
correct.
outside the yellow box.
Correct.
In
Correct.
both CPU and GPU.
Correct, that's right.
And then that can be hacked, right?
Yeah.
So as I understand it, it's outside the TEE, so it's not encrypted by the system, but it's encrypted by a shared key, which is shared between the GPU and the CPU. So although it can be inspected possibly by other actors, there's no way they can decrypt it because it is encrypted by a shared key between the TEE and the CPU and the TEE and the GPU. Is that correct?
That's right, yeah. So the data sitting inside the bounds buffer, even though it can be accessed, it cannot,
It's
it's
encrypted.
encrypted. Yeah.
And the key lies with whom? Whose key is that?
So there is a secure communication happening between the CVM and the GPU. So there are. So there
GPU and
is
CPU.
they exchange keys at the beginning, and then only the parties have the keys to decrypt and encrypt.
Got it. So at the time of bootstrap, whosoever is buying, your customer, will supply the key which will be ultimately used to encrypt the buffers, bounce buffer?
I think it's established as part of the bootstrapping mechanism on a one-off basis for that particular interaction between that CPU and those GPUs, right? So it's part of the protocol for the handshake, for the setup, for the initialization.
Right. Essentially, there are a couple of sessions, SPDM sessions between the CPU and the GPU side. One for the driver itself to use, and that session is established when during the bootstrap, and one from the application side, again, established at the beginning when the application starts. So at that point, the keys are only with the endpoints.
They're ephemeral session keys. Yeah?
Yeah, cool.
You had another question?
Yes. Can we go to the attestation service? Since there were a couple of models, I don't know which one, or frameworks, I don't know which one to choose, but I'm trying to understand. Let's choose one. Yeah, let's choose one.
Yeah.
So the hardware, I'm not sure if it's AMD or NVIDIA, like where's the parameter configuration, et cetera, coming from at the time of bootstrap? Is it coming from AMD? Is it coming from NVIDIA? Where is
So
it
for
coming?
the GPU, there's a hardware root of trust
Yes.
inside the GPU.
Inside the
So
GPU.
that,
okay.
that it makes the measurements, and it also has, it can sign the measurements which comes out. So that comes out of, that is fetched from the GPU by the driver into the CPU using a SPDM session.
Got it. But then that's not enough, right? Because application will need to attest both the CPU and the GPU.
Correct, correct. So for that, Intel actually has this Intel Trust Authority, ITA service.
Yep.
That is the classic example where they are man-in-the-middle service. They also address the Intel attestation.
Both, okay. So
And also
they'll get both
the
the
GPU
attestation.
attestation.
Okay.
They also apparently work with other CPUs as well, non-Intel CPU as well. That's what I was told, yeah.
Got it. So now, let's assume at the bootstrap time, you got the configurations and all that. When an application is running, so there are 2-3 layers, right? There's a hardware level, and probably those configurations don't change. Are there any configuration that changes as the application runs? So at an OS level or something that you attest, and which will make the attestation harder. Like, I'm trying to understand, when does the attestation happen, and when there should be a change, expected change, and when there should be no change in the
I see.
configurations?
I suggest maybe you can reach out to us and we'll see. There's also an attestation session by my colleague Rob Nertney in YouTube. Maybe you can check that out, or you can reach out to us. I can find the answer.
Okay, sounds good.
Yeah, thanks.
I have a question there. Okay, so I had a couple of questions you may not be able to answer. Apologies. Sure. First one is, do you have any plans to be supporting the new ARM CCA realms as that becomes available that you can talk about at all?
Yes, there are definitely plans, especially for next generation CCA, ARM CCA capable platforms.
Fantastic.
But then that's out in the future.
Of course,
so
yeah.
Nothing concrete yet, but yeah.
And the other thing is, again, you may not be able to answer, is all of the things we've talked about here are for on-system GPUs rather than distributed across multiple systems. Are there any plans you can talk about to support off-system GPUs? So, you know, if you might want to use 64 GPUs across 4 different systems, is that supported, or plans for that? Anything you can talk about?
So once TDIS becomes commonplace, once there are NICs which are capable of TEIO and TDIS capable NICs, then you can extend the TE beyond a single node to include multiple nodes, and at that point we'll have a much bigger scale. And that's why I mentioned that, especially with Blackwell, since it is TEIO capable, in the future we can anticipate a place where that will happen, but then it's a while away because we need to have rest of the ecosystem ready.
Of course, so that's already enabled once the other protocols are rolled out across the ecosystem. Fantastic, thank you. Right. Another question?
Regarding this slide, so you mentioned about local verifier and remote verifier. So you mean the remote verifier is something like the Intel Trusted Ultra, or?
No, actually it's a very confusing name. It's just that we had a bad name in the beginning and we stuck with it. Think of it like there is a Python library which the end user has to install in the CVM, and they invoke APIs within that Python library to start the attestation process. So you can either choose to send all the measurements from the infrastructure to the service. The service does the validation and comparison and all that, and then it returns a token. Or you can locally fetch the RIM golden measurements from the service, and the OCSP from the service, and then you can locally do the check. So those are the 2 flavors, but it's probably a misnomer that it's called local verifier in both cases. That can be a bit confusing because even in the remote attestation use case, we have a local verifier box there. I guess that probably put people off, yeah.
Okay, thank you, I see.
Thanks.
Any other questions? Oh, there's one here.
Yeah, it's very interesting to see that with CCON, there is no performance drop when you do Llama 3 inference. Could you elaborate more on this, like why it is not dropping, or what's the main overhead caused by the confidential computing?
Yeah, so it really depends upon the workload, whether it's compute bound or IO bound. sorry, to repeat the question, how can we characterize the performance impact for workloads with convolutional computing? It will vary by workload. And if the data transactions going through the NVLink is in the critical path, then encryption overhead will show up in the performance. And similarly, if the communication between the GPU and the CPU is in the critical path, then we will see bounce buffer impact in that performance as well. So it really varies workload by workload. So that's just one example.
I see. So it's like if there are more I/O operations or more communication between the CPU and the GPU, it will be slower.
Yes, full characterization has not been done, but yeah, it can be. It can be.
It can be. Okay. Yeah. Thanks.
Thanks.
Thank you. Any more questions? Or if not, thank you very much indeed. Oh, we do have another one. Marvelous.
Just think about it. So there are some new technology, for example, the GPU direct storage or GPU direct I/O. So will this be also considered to introduce into this solution?
So the question is new technologies such as GPU direct storage or GPU direct I/O, whether they'll be included in the confidential.
Yeah, so that there's no data transaction need goes through the VM, right?
So yeah. So today we don't. Today we don't support GPU direct storage, for example. The only communication protocol, GPU to GPU communication protocol we support is Nickel. But as customer demands come in, please reach out to us and let us know. Then we'll add.
Okay. Thank you.
Thank you very much indeed, Karthik, for your time. Very interesting. And we will resume in about 15 minutes. Thank you.